We're about halfway through that lifespan. So when the sun starts to run out of hydrogen fuel to make helium, again, the core will destabilize and the outer portion will kind of puff out. It will engulf our solar system, and our solar system will no longer exist. And then that whole thing will be sloughed off as a nebula and will end up as a white dwarf. Okay, so as the stars die, they start to move off the main sequence. All right. So the main sequence is a graph that shows the relationship between surface area and temperature for each star. So red giants move off the main sequence because they have a really large surface area but a relatively low temperature. Okay, so you can see the sun here is hotter than this really large red giant, and the sun will turn into a red giant after the helium's used up. So a red giant itself is a star of great size and age and has a relatively low surface temperature. Nebulas are interstellar clouds of gas and dust, and they're formed after red giants puff up their outer portion, so they'll be a white dwarf right in the middle of that nebula. And that's what you'll see with low mass stars. So this is a white dwarf. It could be about the size of the Earth, and that's what's left over after a low mass star dies. Okay. So intermediate and high mass stars, they'll be between 1.4 and 8 times the sun's mass. Stellar evolution happens quickly. You could have core temperatures of 3 billion degrees Celsius. I can't even fathom that. So the lifespan is much less as a result. So there's more fuel, but it's used up quicker because there's more gravity. Lifespan could be hundreds of millions to a few billion years. So the same thing kind of happens to form it. Gas and dust swarm. Gravitational forces create intermediate mass stars. You have supergiants being created rather than red giants. The star collapses quickly once the fuel is made used up. And the rebound of that star collapsing creates a supernova. And with intermediate mass stars, you'll develop neutron stars and pulsars, but rarely will you get full-blown black holes. All right, so this is a supernova. So the stellar explosion that produces a very bright cloud of ionized gas. It's a very bright object in the sky for weeks to months. We can observe these with the right technology. Super dense star consisting mainly of neutrons formed as the last stage in the stellar evolution of intermediate mass stars. That's what neutron stars are. So all of the protons and electrons are gone and the neutrons are left over. So a neutron star would be here. So very, very, very dense but very small. And this is a pulsar. So some intermediate mass stars will become that. So this is a neutron star that rotates, and it'll emit streams of radio waves. And we can observe that. Okay. So high mass stars, greater than 8 solar masses, they only live a couple million years. So they burn out, they don't fade away. So when a high mass star implodes as the fuel is spent, a supernova does not occur right away. The force continues to collapse, becoming more and more dense. The gravitational field is eventually so dense that light itself cannot escape. So you could have a supernova, but the remnants of that will turn into a black hole. And it is so dense that electromagnetic radiation cannot be released, and you have this empty communication space in a vacuum. Right, so we observe black holes by observing an absence of electromagnetic radiation. We actually observed a black hole for the first time last summer. We observed the event horizon through gravitational lensing and gravitational waves, which was a really big deal in stellar astronomy because it had confirmed a lot of hypotheses that we had about relativity. So we actually know black holes exist because we've seen them. We were able to see electromagnetic radiation being bent at the event horizon of a black hole, or the edge of a black hole. So this is a collapsing star and a high mass star. This will become a quasar. So a collapsing star that releases streams of gamma rays. Okay, and from these observations, we were able to sort of observe the evolution of the universe. So this singularity caused stellar expansion. So before that we had, this multiverse, and this is our universe here, and we're within this gravitational geography. Okay. So we could get real trippy with this conversation, but I'm going to leave it there. That's the end of electromagnetism. I'm going to post this lecture and you have everything you need for Unit 3. So you can do all the assignments now. That includes the unit test, the exposure to radiation assignment, quiz 2. Next week I'll probably post stuff for the last unit, and we'll go from there. Bye now.